In the name of God, the most gracious, the most merciful, praise be to God, and may blessings and peace be upon the messenger of God, our Master Muhammad, and upon all his family and companions. And now, by the declining day, indeed, mankind is in loss, except for those who have believed and done righteous deeds, and advised each other to truth, and advised each other to patience. We now move to calculating the pickup current and timing settings for the distribution protection circuit breaker. We ask, what current will pass through this breaker? In case of a fault, the other cable supplies the feeders. Current here is 200 amps. Pickup current is 125% of this, 250 amps. Convert to secondary using 600.5 ratio. 600 amps primary equals 5 amps secondary. For 250 amps primary, 250 x 5, 600, 2.08 amps secondary. Add 200 menace coordination for trip time. The current here is 200 amps. Pickup current is 125% of 200 amps, equaling 250 amps. Primary. Convert to secondary using 600.5 ratio, 250 amps. Primary gives 2.08 amps secondary. Trip time is 291 millimeters for 5,000 amps, including 200 meters coordination. To find TMS, consider this. To convert the pickup value to Alexandria, the CT ratio used is 600 to 5, meaning that every 600 amps on the primary will give me 5 amps on the Alexandrian. So the value of 250 amps on the primary, how much will it give me on the Alexandrian? By cross multiplication, 250 times 5 over 600 equals 2.08 amps, which is the pickup value on the Alexandrian. As for the separation time here, we increase the coordination time margin by 200 milliseconds as we agreed before. So, the trip time for this feeder is 91.4 milliseconds, and when we add 200 milliseconds to it, the result is 291 milliseconds, which is the time required to trip this feeder when a current of 5,000 amps flows. Now, to find the TMS value, we ask ourselves this question. What is the value that will give me the time when a current of 5,000 amps flows? We agreed that all the circuit breakers used in this station are of a certain type. Therefore, to find the value, we write an equation, which is T equals TMS times 0.4 over I, where I is the voltage for the I setting, which is 0.02. What is the value that will give me the time when a current of 5,000 amps flows? We agreed that all the circuit breakers used in this station are of a certain type. Therefore, to find the value, we write an equation, which is T equal TMS in 0.1 for I volt for I setting power 0.0 to half. The goal of this equation is to find the value that will give me the trip time when a fault current flows. The steps to solve this equation are as follows. First, convert the value to the secondary side. Notice that the ratio used here is 600 to 5, not 200 to 5. To convert the short circuit current to the appropriate secondary, we take 5,000 times 5 divided by 600, which equals 41.667 amps on the secondary. To decide the setting, notice that the ratio used here is 600 to 5, not 200 to 5. To convert the short circuit current to the appropriate secondary, we take 5,000 times 5 divided by 600, which equals 41.667 amps on the secondary. 41.667 amps. Divide 41.667 by the I setting of 2.08, resulting in 20.03. Raise this to 0.02 power using the normal inverse equation to get 1.06178. Subtract 1 from 1.06178 to get 0.06178. Then we take this value and raise it to the power of 0.02 according to the normal inverse equation, resulting in 1.06178. Notice that the 1 appears here again. Focus on the 1. Now from 1.06178, we subtract 1, resulting in 0.06178. We subtract 1 from it, and the result is 0.06178. Then we divide 0.4 according to the equation by 0.06178 to give a result of 2.2661. Now 0.291 equals TMS multiplied by 2.2661. Therefore, the value of TMS becomes 0.291 divided by 2.2661, which equals 0.1285. Now 0.291 is equal to tans multiplied by 2.2661. So the tans value becomes 0.291 over 2.261, or 0.1285. Inspiring the renaissance of a nation. And usually this value cannot be introduced into the narrative as it is. So, when it's entered into the relay converts it to an approximation, making TMS equal to 0.13. Using this new TMS, we calculate the time. Using new TMS and 0.1421. The new time will be 294 milliseconds. For feeder number 1, if closed, the expected trip time when 5000 amps flows from this feeder is the trip time, which is the expected trip time on feeder number 1 is at 0.14 times 20 raised to the power of 0.02 minus 1. The new time will be 294 milliseconds. So, when we move to feeder number 1, if it is closed, the expected trip time when 5000 amps flows from this feeder is the trip time that exists on it. So the expected trip time on feeder number 1 is, and then we ask ourselves the same previous question. What is the value? That will give me the trip time when a fault current of 5000 amps flows. To achieve a trip time, when a fault current of 5000 amps flows, to find the TMS value, we substitute into the normal inverse equation, which equals 0.49, where TMS is 0.14 for any fault with a setting strength of 0.02 minus 1. Notice here that there are two variables we haven't calculated yet. These are the I volt and I setting. Now let's calculate the I volt and I setting, and then we'll go back to calculate the TMS value. The expected fault on this feeder is 400 amps because we mentioned that this feeder is fed either from this feeder or from that feeder. Therefore, the pickup current value is 125% of 400 amps, which equals 500 amps. Of the 4 buildings, 5 are grilled. This 500 amps is the pickup current. To convert to the secondary, use the city ratio 600 to 5. 500 amps converts to 4.17 amps. The fault current is 5000 amps, converting to 41.67 amps. Let's calculate the TMS value. You need 3 key details. The trip time for the TMS value, 5600 and equals. The fault current value here is 5000 amps. To convert this value to secondary, we say 5000 times 5 divided by 600, which equals 41.67 amps. Now let's go back to calculate the TMS value again. Focus with me. To calculate the TMS value, you need to have 3 basic pieces of information. The first piece is the trip time at which you want to calculate the TMS. To find TMS, equate 0.4 to TMS times 0.4 over 41.67 divided by 4.7, all raised. To find TMS, 0.4 equals TMS times 0.4 divided by 0.4 over 41.67 divided by 4.7 to the power 4167 I fault current. High 417 002 1 hour TMS 014 10 002 1 049 TMS 014 1 047 1 all raised minus 1 10 raised minus 1 0.49 TMSX 0.14 1.047 minus 1, 10 minus 1. 0.49 equals TMS in it. 0.1 for 1.0 for 7 minus 1. 0.39 TMS x 0.4 0.0 0.4 From this, 0.494 equals TMS times 2.9705. Therefore, TMS is 0.494 divided by 2.9705, approximately 0.17. Now calculate the new time value from 0.7. The trip time at TMS 0.7 equals 0.17 times 0.14 over 10 raised to 0.02 minus 1, which is 0.505 seconds or 505 milliseconds. Next, set the overcurrent relay on the secondary side of the power transformer. When setting the pickup current, it's better to calculate from the rated current rather than the maximum load current. Both are correct, but the rated current is commonly used in power stations. 0.17 times 0.14 over 10 raised to the power of 0.02 minus 1, which equals 0.505 milliseconds, 0.505 milliseconds. Set the secondary side over current relay. For pickup current setting, calculate pickup from rated current, not maximum load current. Both are correct, but this is common in power stations. Pickup is 150% of I rated. I rated is megavolt amperes over SQR3 times phase voltage. Here, 25 MVA over SQR3 times 11 kV equals 1312 amps. So it should be 150% of the I-rated current, and the I-rated here is calculated using the well-known aberrant power equation, which equals megavolt amperes divided by the square root of 3 times the phase-to-phase voltage. In this example, it equals 25 mega volt amperes divided by the square root of 3 times 11 kV, which gives us 1312 amps. This ratio for the pickup current value of the overcurrent relay installed on the transformer is set under the assumption that the maximum load on the transformer is 120% of the full load value. We took 125% of the maximum load, which is 125% of 120% of the full load, equating to 150% of the full load, which is equal to 150% of the flood. 150% of 1312 amps is 1986 amps. About 2000 amps, the primary pickup current. Convert to secondary using 1500.5 ratio. 2000 amps times 5 divided by 1500 equals 6.66 amps, the secondary pickup current. Trip time must exceed the overcurrent relays by 200 milliseconds, which we'll calculate. If 2000 amps times 5, 1500 equals 6.66 amps. Trip time must be 200 ms longer than the bus section relay. If feeder 4, fed from transformer 1, fails, the bus circuit breaker must trip with a 200 ms margin. If F14, fed from transformer 2, fails, F14 must trip first. If it fails, F1, then the bus section, and finally T2 must trip. Calculate bus section relay settings first. Assume max current through the bus section breaker, and feeders are supplied from the other transformer through this breaker. This feeder was supplied from transformer 1, so this bus section is closed. If feeder force protection fails, the bus section circuit breaker before the transformer must trip. If a fault occurs on F14, supplied from transformer 2, F14 must trip first. If that fails F1, then the bus section, and finally T2 must trip. Calculate the bus section overcurrent relay settings first, then return to the relay. Assume the maximum current. So F14 must trip first. If that fails, F1 must trip. If that fails, the bus section must trip, and if that fails, T2 must trip. Now let's calculate the settings for the bus section overcurrent relay first, and then we'll return to the relay again. We want to assume that the maximum current that will pass through this bus section circuit breaker occurs when one of the transformers is disconnected and the feeders are being supplied from the other transformer through this bus section circuit breaker. We assume the bus section circuit breaker's pickup current is 2000 amps, like the transformer. Converting 2000 amps to the relay's secondary side with a 2500.5 ratio gives 4 amps. Using 2000 x 5, 2500. The I fault current of 5000 amps converts to 10 amps on the secondary side, calculated as 5000 x 5, 2500. The trip time exceeds feeder trip time by 200 milliseconds. The bus section circuit breaker's trip time is 0.505 plus 200 milliseconds, totaling 0.705 milliseconds. Coordinating with feeder trip times ensures proper timing. The value is 10 amps. The trip time is 0.705 millis, coordinated with feeder times. Aligning with feeders 4 and 5 conflicts with F1's 500 millimeters. Consider all current flows. The bus section circuit breaker trip time is 0.705 milliseconds. Why was this coordinated with the feeder's trip time and not vice versa? This is logical. Coordinating with feeders 4 and 5, each 200 milliseconds increases trip time to 400 milliseconds. This conflicts with F1's 500 milliseconds if current flows this way. Thus, consider all current flow scenarios. Thus, the overcurrent relay trip time on the transformer's secondary side is 0.905 seconds. The trip time for feeders 4 and 5 is 200 milliseconds. So the trip time will increase by another 200 milliseconds, making it 400 milliseconds. This 400 milliseconds conflicts with the 500 milliseconds on F1 if the current flows this way. Therefore, we need to consider all the expected scenarios for current flow. So the trip time for the overcurrent relay installed on the secondary side of the power transformer is 0.705 seconds plus 200 milliseconds, which becomes 0.905 seconds. This becomes 0.905 seconds when you add 200 milliseconds to 0.705 seconds. In the same way as before, we ask ourselves what the TMS value is for the normally inverse curve that will give a trip time of 0.905 seconds when 5000 amps are flowing. To find the TMS, we need to have prior knowledge of 3 values. The first value is the trip time. The second value is the I fault current value on secondary or primary. And the third value is the I setting current. The disconnection time is 0.905 seconds, while the I fault current is 5000 A. As for the fault current, it's 5000 amps. To convert this value to the secondary side for the CT ratio here is 1500 to 5. So we say the I fault on the secondary side is 5,000 times 5 divided by 1,500, which gives me 16.667 amps. As for the I setting value, it's 2,000 amps, so it gives me 16.667 amps. And as for the value, it's 2,000 amps. As we mentioned before, to convert 2,000 amps to the secondary side, we say 2,000 times 5 divided by 1,500 equals 6.667. Now we will substitute these three values into the normal inverse equation because we agreed that normal inverse is used in all the relays in this station. So we say 0.905 equals the unknown TMS, which we need to find. We say TMS is the unknown value that needs to be found. 0, 14, 16, 17, 6, 0, 0, 2, 1, 6.67 raised to the power of 0.02 minus 1. Therefore, 0.905 equals TMS times 0.14 divided by 1.0184 minus 1. Thus, 0.905 equals TMS times 0.14 divided by 0.018488 minus 1. Therefore, 0.905 equals TMS times 0.10 divided by 1.0184 minus 1. So 0.905 equals TMS times 7.5722, which means the value of TMS is 0.905 divided by 7.5722, giving us 0.1195, which is approximately 0.12. The TMS value of 0.905 divided by 7.5722, 0.1195. The new trip time value at the new TMS after rounding is 0.12, 0.14, 0.018488, 0.908 S or 908 ms. For feeders 3 and 4, when the bus section circuit breaker is open, these feeders are supplied from transformer 2. When the bus section circuit breaker is closed, these feeders are supplied from transformer 1. 0.12 times 0.14 divided by 0.018488 equals approximately 0.908 seconds or 908 milliseconds. As for feeders 3 and 4, there is an important scenario. The first scenario is when this bus section circuit breaker is open and these feeders are supplied from transformer 2 as shown in the diagram. The second scenario is when this bus section circuit breaker is closed and these feeders are supplied from transformer 1. This is the scenario we will discuss now. When a fault occurs on feeder number 3, the fault current will flow this way. Therefore, feeder number 3 must trip first. Now, if we assume that the fault current value here is 20 kiloamps, this feeder should trip in the shortest time possible. In order to separate this feeder in the shortest possible time, we choose the normal inverse curve, and its TMS is the lowest possible value, which is 0.05, and it goes to 0.5. To find the expected trip time, you need to know three essential pieces of information: the TMS value, the I fault current value, and the I setting value. The TMS value we chose is 0.05 to achieve the shortest possible trip time. As for the I fault current value, we assumed it to be 20 kiloamps. This value can't just be assumed randomly. It must be determined from a short circuit calculation or from ETAB software or from the following programs. Convert 20 kiloamps to the CT secondary side using the CT ratio of 600 to 5. The I fault current on the CT secondary side is 20 kiloamps times 5 divided by 600, equaling 166.6 amps. The I pickup current for this feeder is 125% of the maximum load current of 400 amps, equaling 500 amps. Convert 500 amps to the CT secondary side using the same CT ratio, resulting in a pickup current of 4.166 amps. After determining these values, calculate the trip time as T water 0.05 TMS value times 0.14 divided by 125% of the maximum load current coming from this feeder, which is 400 amps. So we say the pickup current is 125% times 400, which equals 500 amps. Then we convert this 500 amps to the CT secondary side. We said that the CT ratio here is 600 to 5. So the value of the pickup current on the CT secondary side is 500 times 5 divided by 600, which equals 4.166 amps. After finding these three basic values, we calculate the trip time, which equals T, equal to 0.05, which is the TMS value times 0.14 divided by 0.5, which is the value in 166.6 amps, 4.166, 0.02, 1 grounding, 0.05, 0.14, 40 by 0.02, 1 grounding, 91.4 milliseconds at 0.14 over 40 to the power of 0.02 minus 1. And so the value of the time of the trip is equal to 91.4 milliseconds. And in this way, the value of the time of the trip is equal to 91.4 milliseconds. And in this way, We found values for all relays. The engineer receives a summary table, inputs specific values, and checks safety. Curves are in ETAP software. For time coordination using the definite time curve on overcurrent relays, it's easier. Coordination follows the table with pickup current values and trip times. Feeders 1114 have a pickup of 125 A and trip time of 200 ms. The bus section circuit breaker has a pickup current of 300 A and a trip time of 400 ms. To coordinate time using only the definite time curve for all overcurrent relays is simpler, as it avoids using various inverse time curve equations. Coordination follows the table showing pickup current values and trip times. The time gap or margin time between stages is 200 ms. Feeders 1114 share a setting. 125 A pickup on the primary, 200 ms trip time. The bus section circuit breaker has a 300 A pickup current and 400 ms trip time. Feeders 1 and 2 also share settings. 500 A pickup, 600 ms trip time, maintaining a 200 ms gap between stages. The bus section circuit breaker has a 2000 A pickup on the primary and an 800 ms trip time. The bus breaker pickup is 300 amps and its trip is 400 milliseconds. Feeders 1 and 2 share a setting of 500 A pickup and 600 ms trip with a gap of 200 ms between stages. The bus breaker pickup is 2000 A primary and its trip is 800 ms. Feeders 1 and 2 share a setting of 500 A pickup and 600 ms trip with a gap of 200 ms between stages. The bus breaker pickup is 2000 A primary and its trip is 800 ms. The circuit breaker is 2000 amps on the primary and its trip time is 800 milliseconds. As for transformers 1 and 2, they also have the same setting with a pickup value of 2000 amps on the primary and a trip time of 1000 milliseconds. For feeders 3 and 4, their pickup current on the primary is 500 amps and the trip time is only 200 milliseconds. The revival of a nation